Hi everyone, in this video I'm going to talk about refinement as it pertains to Riemann integration. The main theme of this video is that if you refine a mesh, you're essentially truncating it into smaller and smaller pieces, and as you learn in calculus, as you refine the mesh smaller and smaller, you should converge to the integral. And so we're just going to build a basic tool to help prove things later on. So just for a definition of a refinement, it's relatively intuitive. If you take an interval I, our typical setup, P is the set of partitions over I, and we take two partitions, P and Q, with P indexed from 0 to N and Q from 0 to M, then we say that Q is a refinement of P whenever, if you give me any index in P, in 0 through N, I can always output an index in the Q partition such that their values match. So that is, for every j, there is for every j between 0 and n, there is an I sub j in 0 through m, such that Q sub I sub j equals pj. So just as an example of this, if we take P to be this coarse mesh here, 0, 1, half, 1, so just these points here, uniformly spaced, and we take Q to be equal to this set, this partition, then we see that Q is a refinement. Why? Because if we ignore this picture I have down here, we start with 0. We can do this systematically. Is there a value that's equal to 0? Well, yes. Of course. So the left and right endpoints are always going to be satisfied if Q is a partition, right? Because if that's not even satisfied, then one of them's not even our partition. So we go to 1/2. And basically we're asking, well, is there any point in Q that's equal to 1/2? Well, yes, it's index Q sub 2 here. And that proves that it is a refinement. No matter how, so the rest of these don't really matter, but we do see, since we match on this point, and this point, then if we add some extra points, well, it's just going to make the mesh finer. That's the idea behind refinement here. So we're just going to prove one result in this video. It's sort of a basic building block that we're going to use over and over for the remainder of this section. So our typical setup, F from I to R, P is a set of partitions, P, same setup, 0 through N, Q, 0 through M, with Q being the refinement of P. Basically what this is going to say is that we expect, as we refine the mesh, to get closer and closer to the real value of the integral. In other words, that the lower sum, the lower Darboux sum, converges to the upper Darboux sum. But this is in a finite sense. So we know that basically what we're going to show is that the upper integral decreases with refinement, right? Because we're taking the infimum of the upper integral. Clearly the upper integral should be bigger than the lower integral here on the same mesh. And that since we're taking the supremum of the lower integral, it should increase under the refinement operator, not Q, P. So as we refine the mesh, the lower integral increases. So it's a fundamental property, and you can see why we're going to use this tool over and over again. So I'm just going to show the upper integral here. So just a bit of notation. I'm just going to call this to be the supremum. You can see different notations in other places. And then the bar below to be the infimum on this interval. It just saves space. If you want, you can write it out if you don't like that notation, or find another notation that you want. So I'm just going to explicitly say, since Q is a refinement, of P for J between 0 to n, let ij between 0 and m with q sub I sub j equals p sub j. So I've now enumerated essentially that map between p and q. And I'm starting to run out of space here. So we're going to have some inequalities, so I'm just going to go to a new page here. So we have q sub I sub j equals pj. That's basically where we're at. And I'm just going to compute this sum here. Well, this is just, by definition, so again, this bar being on the top just means supremum. Oh, that's an ugly p. pj minus 1. Okay, and we're just going to do some just some small algebraic manipulations, nothing too fancy here. But might not be immediately obvious to you. So we're going to take advantage of this property here. That property is really why refinement is the object, why we define refinement that way. So I'm going to do this in purple. Actually, let's write this out. So I'm going to do a telescopic sum. But let's just write this for now. So you can certainly agree that that's equal, right? Because it's just direct substitution. I just change my indices, and we're going to move to the left. We're going to squeeze more inequalities per line here. So this is the sum, j equals 1 to n, f bar of pj minus 1 to pj. Let's switch back to purple. And now I'm going to do a telescopic sum here. And I'm going to write this big to make these sub-indices more obvious. So this is I sub j minus q sub I sub j minus 1 on the top, plus we have to add it back because we subtracted it. J minus 1 minus q sub I sub j minus 2, and so on. We have to add that one back, and then q sub I sub j minus 1 plus 1 on the top. In fact, let's just, so this is minus 1 on the top, minus 2 plus 1, just to be explicit there that the j is in the sub-index there. Minus q sub I sub j minus 1. So that's just a telescopic sum. And now I'm just going to write, so if you agree with that, that's just a telescoping sum. Common trick. And I'm going to write this as k equals I sub j minus 1 plus 1 on the top. That's why I'm doing that one in purple. Oh, no, not to m. To I sub j. And if those indices, if you disagree with them, pause the video here and convince yourself that those are right. And if they're wrong, please leave a comment in the comment box. So this is now q sub k minus q sub k minus 1. So that indices, so now those indices are relatively simple now. Okay, so then this is the key point. This is the key trick of the proof, beyond that telescoping sum. That's a small trick there too, is that p sub j minus 1 to p sub j Sorry. Well, yeah, I guess I can. P sub j minus 1 to P sub j. This is a coarser grid, right? So if I take Q sub k minus 1 to Q sub k for k between I sub j minus 1 plus 1 to I sub j, then that subset relationship is true, which tells us that f bar pj, you can pause it here. There's an inequality. We're taking a supremum. So again, this is basics. Make sure this is straight in your head. Pause the video here. This will be greater than or equal to that because it's a bigger set. So I'm going to write greater than or equal to this sum. Plus 1 on top here, just to make sure the indices are correct. And now this is f bar of qk minus 1, qk minus qk minus 1. And now this sum, what we're really summing, right, is let's call this alpha sub k, right? And this is the right term for a Riemann sum, or, well, for a Darboux sum, right? What we're doing is we're indexing over q sub I sub 0, q sub I sub 0 plus 1, q sub I sub 0 plus 2, and so on, to q sub I sub 1, to q sub I sub 1 plus 1, to q sub I sub 2. And remember that this is equal to, let's just stick with yellow. This is equal to P sub naught. This is P sub 1, P sub 2, Q sub I sub n. It's P sub n. So we're just writing it slightly differently, but we see that this is summing all the way from 0 all the way up to m. So this is just equal to, and again, if you get a bit confused with the indices here, that's totally natural. Pause the video and convince yourself of this sequence that I've written, that you are listing them as you normally would if you were computing the upper integral. And then this expression is exactly q. And then at the very end, that was all equalities. This was our only greater than or equal to. And so that tells us that u of fp, the upper integral, decreases with refinement. And similarly, I'll leave this to you guys, that the lower integral increases with refinement, and that completes the proof. Keep this result in mind. This is a basic building block for proving the main result that we'll show with Riemann integration in this section. Thanks for listening.